Okay, we're on number 3 on the 5.4 worksheet, and this is the problem that gave everybody the most trouble. And I think the reason is it's hard to determine when the starting year is, because they mention it's kind of all over the place, this problem. It says it's been decaying for 5 years, right? And then it starts talking about what happened 3 years ago. 3 years ago, you had this much, and then what we have now. So if we're using years, for instance, what would be the green year if we're talking about now? Well, what year is it? In 2012, there's 5.2. What about 3 years ago? 2009, there were 6.0 grams of the material. How much was there 5 years ago? We don't know. So we really need to determine what the starting point's going to be. And in the equation y equals ab to the x, that's kind of important to know what a is, to know what the starting amount is. So I think for the purposes of practicing another topic for tomorrow's quiz, we should do this using that point ratio form, okay? Where you treat the starting year, the red one, as our A. So we don't know what that is yet. And since we don't know how much there was in year 0, we have to go to this point ratio form, and that is this. There was a homework problem last week using point ratio form, and not sure, we really didn't formally talk about it all that much in class. So there have been a couple of videos, though. If you look up on channel 5.3 on the multimedia page, point ratio, there are 2 videos on there. So what this does is it allows you to find the growth rate without knowing what you started with. So without knowing what A is, you can still find B. The trick is you have to write 2 equations. So we're going to use the blue numbers as point number 1. So you need to know, first of all, if 2007 is year 0, what year would 2009 be? 2. And what would 2012 be? 5. And when we go to part D, how much would there be after 50 years? Part D, we're actually going to plug in 50, because it would have been 50 years. Yeah, 50 years from 2007. 2007. Good? So that's going to be 50. If we would have used today as our base year, they're saying that it would have been 45 years from now, but we're not. We're going to use 2007 as year 0. So here's how point ratio works. I'm going to use the blue information to make a blue equation. The y that you get is based on the y value they gave you. There were 6 grams that year, times b to the x minus how many years? 2. And then the green equation. Y equals, there were 5.2 grams left, times b to the x minus, how long did that take? 5 years. Now we can use both of those equations to solve for b. So we're going to get the decay factor. And then eventually we'll turn it into the decay rate. So there's a lot going on in this problem. So what we do next is we say, well, both of these equations equal y, so we're going to make them equal each other. If 2 equations equal the same thing, you can make them equal each other. That's one of the common properties that we use all throughout math. At this point, you can decide, would you rather divide both sides by 6 or divide both sides by 5.2? I'm going to go the other way, and I'm going to divide both sides by 6. All right? The reason I'm going to do that is I know this problem is about decay, right? I know that my decay factor is going to be less than 1. I want it to be a decimal between 0 and 1. So what will give you a decimal between 0 and 1? Dividing both sides by 5.2. Is 6 over 5.2 something less than 1? No, it's greater than 1. If I divide both sides by 6, what's 5.2 divided by 6? Give me the actual answer. 0.86 repeating. Is that less than 1? That's where I want to be. I want to be there because this is a problem about decay. If it was a problem about growth, I would have divided the other way. That won't make or break your problem, all right? You'll be able to still get the right answer if you would have divided by 5.2. I just think it's going to make more sense this way. So these cancel, and I get b to the x minus 2 equals, you said 0.86 repeating. Does everybody agree on that? So I'm going to call that 0.867 b to the x minus 5. This is 0.867. The b to the x minus 5 is still there. Next, we're going to divide both sides by b to the x minus 5 because we don't want it to be over here anymore. We want it to just be a number. And this is where on the first video for point ratio, I stopped and I made you finish it on your own. Then I produced another video where I completed this process. So if you haven't watched them yet, I suggest you do. Again, they're on 5.3 point ratio. On the right side, you're just left with 0.867. And on the left side, you have b cubed. Now, while you sit and think of why, I'm going to remind you of this rule. What's b to the m over b to the n? B to the m minus n. Very good. So you subtract these, right? Well, what happens when you subtract the x minus x? 0. Well, what's negative 2 minus negative 5? Double minus 3, right? Negative 2 plus 5 is 3. So that's where that exponent 3 comes from. Now, how are we going to get rid of it? Cube root or raise both sides to the 1/3. So whatever you have on your calculator, you have that 0.86 repeating, right? Just hit caret 1/3. Take it to the 1/3 power, and you're going to have your b. It should be smaller than 0.867. Oh, bigger. 0.953? Okay, there we go. 0.953. That's right, because we're raising it to the 1/3, not the third. All right. 0.953. That's the decay factor. You could have gotten that answer multiple ways. All right. I wanted to do it this way so that we could practice this point ratio idea. Okay. That's not the decay rate. For the decay rate, you do the same thing we did where you knock off the 1 and multiply by 100. Except what's going to happen when you take away 1? It's going to be negative because you're losing that amount. That's why it's negative. Did you get negative 0.047 times 100 is negative 4.7. Did we round before? So it's about 4.7% decay. That's the decay rate. And what question was that? A. All that for part A. For how much was initially in the sample? How much was initially in the sample? What do you think? 6.59? How do we know? I'm going to pause it while we discuss it, and then we'll continue the video. Think about how we're going to go back now and find that initial amount. We're looking for this guy right there. So to find out how much material there was 2 years before 2009, here's what we're going to do. We're going to treat y equals 6.0 as our base amount, 0.953 as our decay factor, and for time, we need to think about how many years ago 2007 was compared to 2009, and we're going to put in -2 because it was 2 years in the past. 2 years in the future would be positive, 2 years in the past negative. Calculate it, and you'll get the red y value. B is the growth factor, not the rate. Yep. So 6.0 times 0.953. Whoa. Not working. What'd you get? 6.6 grams. That's how many grams were in the sample 2 years ago in the year 2007. Find an equation to model the decay. So for part C, let's use y equals 6.6 times 0.953 to the x. How much is in there after 50 years? Plug in 50. See what you get. And E, what is the half-life of this radioactive material? That means how long will it take to cut in half? So we're going to do both of these problems using our graph on our graphing calculator. So I'm going to pause the video, and you should too, if you're watching from home, and then watch the answers. Okay, we're back, and we have y1 being 6.6 times 0.953 to the x, and that is using 2007 as year 0. If you used a different one, then you would use a different starting amount, and you would be looking for a different half-life. All right, so you have to know what your starting year is and how many years past that you're looking for. What are we looking for using 6.6 as our base year? Well, let's go to Window, and let's go to, by the way, the answer to that question is 50. We want to make x 50. So what should I put in for x max? Something bigger than, all right, I'm going to put in 55 years. Then, for y max, what's going on? What kind of graph do you expect to see? A line or a curve? Starting where? What was our starting amount? 6.6, right? And then decaying. What will it never pass? If something is decaying exponentially, it'll never pass 0. So actually, a window here for y of 0 to 10 should be sufficient. Let's see what it looks like. We should see a decaying curve and the horizontal line at 3.3. There's the curve. And here comes the 3.3 coming across. The answer to question D will be trace 50 years. Enter. Looks like there's about 0.594 or 595 grams left after 50 years. The answer to E is the half-life. We want to find this intersection right here. Second trace. Second trace. Option 5, enter, enter, enter. The half-life should be 14.4 years. That's how long it takes for half of it to go away.